and I admit everybody.
Okay, let me wait 1 minute. Okay, so let's get started. Thank you everyone for joining us for the first session for this academic semester for the virtual seminars in economic theory. We're very happy that you're back here. Today we start with Philipp Strack, who is going to talk to us about non-discriminatory personalized pricing. It's a joint work with Kai Hao Yang, who's also here. And we're very happy to have our guest panelists, which is Laura Doval and Alex Smolin. The format of the seminar is as follows. We have a 60-minute presentation with time for interim questions from the panelists. We encourage the audience to participate. You can post comments and questions in the chat. There's going to be an opportunity to ask questions live in the Q&A session at the end. And you can also unmute yourselves if you want to ask a question during the talk if it is important. Just a reminder that the talk is recorded. And just before I hand over to Philip, just let me announce the next talk, which is by Maria Giovanna Baccara, who's going to talk about research waves with Gilad Levy and Ronnie Razin. And the guest panelists are Steve Callender and Julia Salmi. Thank you, Philip. The screen is yours.
Yeah, thanks a lot for inviting me. And yeah, thank you, Laura, and thank you, Alex, for joining and being a discussant. So most important, the paper is a joint work with Kai Hao, who's also here, and it's on non-discriminatory personalized pricing. So the question which we want to address is, suppose you are a seller and you have very rich consumer data, but you are not allowed to use certain characteristics to price the product, such as gender or race, which is illegal in many countries. So just to give you a brief overview, the idea behind third-degree price discrimination is that you might be charging different prices to different segments of consumers. But for example, you could be charging different prices in different locations. That's what some supermarkets do. You could try to charge different prices to different age groups. If you think that some product is kind of maybe tailored to a specific age group, it might be priced differently. And you might also try to charge different prices based on occupation or other characteristics you observe. In many countries, there's limits to that. So you cannot arbitrarily use characteristics to determine your prices. And for example, in the US, race and gender are off limits. And so price discrimination based on these characteristics is typically illegal. This does not only mean that you cannot directly use these characteristics, but it's also very restricted how the prices which these groups see can differ across groups. And I will give you more context a little later. And the question we ask is just very simple. How should a seller set prices given that there's limits to the extent to which he can price discriminate between two different groups? And a bit more specifically, we're going to ask this when the seller has a lot of data. And what we are interested in is what are kind of the welfare outcomes of these regulations. We think to even think about these regulations productively, we need to understand what a profit maximizing seller will do if he faces these regulations. And then once we understand that, we can ask ourselves what are the welfare outcomes, and then we can ultimately, that's important to understand whether we want such regulations or we don't want them. Yeah, so this is the goal of the talk and what we aim at doing. Yeah, please interrupt at any point in time. So just warm up where we can look at the case, which is kind of a classical case of third-degree price discrimination. Suppose there are two groups indicated by theta in 0 or 1, and that's the only information available to the seller. So he observes this group identity, and suppose kind of the demand curves for the two groups are as depicted in the picture, then the seller would want to charge different prices to these groups. and these groups would be facing different prices. And if there would be regulation which would make price discrimination based on group identity illegal, then the seller would charge the same price, and the group with kind of the higher willingness to pay would typically benefit, and the other group would suffer from that. Yep. So yeah, then there would just be some average some price charged in between to both groups, and that might be to the benefit of one group and might hurt the other group. So what we are going to ask is, we are going to ask for a seller who has much more data. He is not going to only be able to see the group identity like gender, but he's going to see a ton of other stuff, and he's going to use that information essentially to be able to predict valuations. So especially if the seller has a lot of other data, then he can actually discriminate based on group identity, such as race, even without using race as an input into the algorithm explicitly. So how does this work? Well, race can be predicted extremely well from other correlates, such as zip code. And this is widely recognized. And so here's a quote from the White House on differential pricing, which makes this point explicit, that we might be using correlates of gender, race, ethnicity, or religion, even if we don't use gender or race explicitly as an input into the algorithm. And the point that the legislation from the Obama administration makes is that that's also illegal. So even not using it directly as an input, but indirectly. So that asks the question, what is actually the set of things the seller can do? And what the legislator in the US at least has decided on is that a practical thing is to test whether prices are statistically correlated with characteristics. Even if prices are not direct, like don't use characteristics directly as an input, which is very hard to test also for the legislator because he doesn't know the algorithm the firms are using. What the legislator can test is actually whether there's statistical correlation. And that's made very explicit in the same White House report, which kind of says that the way you could test this is to conduct statistical tests for correlation. And so the explanations to the laws from the Obama administration are very explicit that what they want to test for is correlation between prices and these characteristics. And so we are going to follow the US legislation in saying that kind of the pricing is discriminatory if the distribution of prices is different for across protected groups. And we want to ask what type of market segmentation maximizes the seller's revenue if he doesn't want to violate the law. Any questions? Okay.
I guess I can ask one clarifying question. So he will think about the revenue maximizing seller. So it will not be malicious seller who deliberately wants to hurt particular group.
No. But the seller has no preferences over these groups. He just wants to make as much revenue as he can.
Exactly. But doing so, she can hurt particular group. Yes.
Yep. So I think one extension of the model is where the seller might like care differentially about these groups and their welfare, and might even put negative weight on some groups. And this is something which I think you can do using very similar methods. So I don't have it in the slides, but I think we will have it at least in some version in the paper where the seller cares about the welfare of these groups. But here in the talk today, it's just profit maximization. But I think the question is very natural when the seller might care about these groups. Yeah.
Great.
So Philipp, hi. So what about, I'm wondering in your first example, imagine you don't have unit good. Maybe you could offer, instead of offering an average price, you could just offer kind of a menu, and the two groups would self-select into different prices.
Yep.
So, you basically pretend, okay, this is like private information, even though it's not private. So how is that considered? And
So I think you will see it a little bit later if you see what the seller is doing. If you're asking me whether this is what this legally is,
I guess there are two questions, on the theory part. So, is this somehow, allowed?
On the theory part, I think, answer the question a little bit, and you will see this in like a few slides. On the legal part, I mean, there is a lot of debate on what this anti-discrimination legislation means, and if the seller induces self-selection by the customers, if this still can be discriminatory. I'm not a legal expert, but that's at least debated whether that still can be discriminatory. So yeah, I can't answer the legal question.
Yeah, that's fair enough. Yeah.
I don't even know if that question is actually set. I don't know if there is an answer, a definitive answer to that question, but I think it's a very good question and very important to understand. I think if the seller, I think my view of reading these reports is that everything which essentially makes the legislation toothless will probably be then if the seller can make the legislation toothless through self-selection, probably the legislator will interpret the law in such a way such that it's not toothless. But yeah, I don't know. I'm not a lawyer. Yeah. Okay, so then there's a kind of large related literature. Most closely related is the literature on market segmentation and third-degree price discrimination. And I think there are two papers which I think especially related. So there's a paper by Cohen, El Maktoub, and Lay, which looks at the case where the seller doesn't have rich information and he sees the characteristics and he can price their limits to how different prices he can choose. And then there's another paper by Pala, Jordan, Makdumi, and Malekin, which looks at a different notion of privacy, where I think the values get added noise, but I'm still in the process of better understanding the whole literature. So if you have any references or things which we forgot, then yeah, please just tell us. Then what's also very related is to this work is the idea of privacy preserving signals, which was developed in Yale, Sandomierski, and Temuz. And we also wrote a paper developing that idea. And here, the idea is that signals need to be independent of certain characteristics. And as you will see a little bit later, that just plays mathematically a key role in the analysis. And we're going to use the result from our earlier paper as a key step of the proof. Then there's a large literature on optimal transport. As you will see, optimal transport methods show up in the talk, and we will actually be able to solve kind of a novel optimal transport problem, and I will show you a little later. And then there's a literature which is kind of conceptually closely related also on algorithmic fairness, where especially Laura and Alex have a recent paper in this literature. Perfect. So then if there are no more questions, then maybe let me show you the model and things become hopefully clear. So we're going to start with some probability measure, which is going to be a joint distribution over the value an agent has for the good and their type. And they're just going to be two types. You can think of them as two races, like black and white, male and female. But the type is going to indicate a protected group, and the value is going to be the willingness to pay for the product a consumer has. We're going to assume that there's a unit mass of consumers. Each consumer wants one good, and the theta, the type, is going to indicate the protected characteristic. We denote by f theta the distribution of values, the cumulative distribution conditional on theta. We assume that this distribution admits a density, and we're going to assume that the type theta equal to 1, which we're going to call the high type, has higher values in the likelihood ratio order. What that means is that they have higher values in first order stochastic dominance, and that the demand of the low-value customers is more elastic than that of the high-value customers. And then we're going to consider market segmentations by the seller. And so we're going to start with some space S. And a market segmentation now takes in a value of a given buyer, their characteristic, like male or female, and potentially some random number, and then attaches them to a segment. You can think of this that each type consisting of their protected characteristic and value, some get added to that segment, some get added to this segment, and you might split some types into multiple segments randomly. Yeah? And this is completely equivalent to saying that the seller observes a Blackwell experiment about the buyer. So he observes some signal about the buyer. This is just mathematically equivalent. Just in this literature, this was called market segmentations, but mathematically it's just the same. And now what can the seller do in terms of pricing? Well, in each market segment, or if you want to stay with the idea of Blackwell experiments, for each signal realization, the seller now solves the standard revenue maximization problem, which means he wants to maximize over prices, non-negative prices, the price times the probability the buyer is buying, and that probability is evaluated conditional on the signal or market segment this buyer is in. By the way, can you see my cursor? Perfect. Yes. Okay, and then this is very standard. The profit of the seller is just the expected amount of money he makes given optimal prices, and the pricing rule or an optimal pricing rule is a function such that in each segment the seller uses an optimal price. Yeah. And so an outcome of a segmentation and a pricing rule is a joint distribution of values, protected characteristics, and prices people face. A segmentation is non-discriminatory if in this segmentation there exists an optimal pricing rule such that the distribution of prices is the same for the high and the low types. They just face the same prices. So they statistically, you could not distinguish, you cannot learn from seeing the price anything about whether that's a high or low type. And this is exactly the notion which was also suggested in the Weishaus report for what it means practically to be non-discriminatory.
Sorry, Philip, segmentation is exogenous?
No, the seller is going to choose it.
Okay, thanks.
Yeah, that's a very good question. And so our question is, suppose the seller wants to kind of now comply with the law. What's the non-discriminatory market segmentation that maximizes the seller's profit?
Philip?
Yep.
So I understand this is like the definition that comes from the law. But I'm guessing that given the ordering, the different ordering of the consumers,
yep,
then higher value, this favors higher value consumers of type 1 because they're more likely to get lower prices than high value consumers of type 0. So how you guys given that this comes also from thinking about disparate impact.
Yeah, exactly. So this is actually a very good point, and you are far ahead in the sense that the law has an intent, I think, of protecting low value type 0 consumers or type 0 consumers. But and actually, if you read the discussions, whoever made the law assumes that this will be the effect of the law. But I think to understand whether that's indeed the effect of the law, you need to understand how a seller will react to that law. And that's exactly the question we set out to ask. And you're completely right in predicting that maybe the law doesn't achieve exactly the effect the lawmaker intended. And yeah.
Oh, okay, sorry. So I did not mean to jump ahead. I was just thinking that if they face the same price distribution just because one distribution is different from the other. But you're saying that this will come as a result of this, how the seller segments.
Yeah, so this will be driven by how the seller segment.
Sorry.
No. This is this is a very good question.
I thought it was the likelihood rate, the likelihood ratio, the monotone ordering across the distributions gave this. Sorry.
Yeah, no, I mean, but this is, I think conceptually, this is exactly the question we should be asking is what are the effects of these laws? And I think here we can also be useful as economists because maybe some of these laws don't have exactly the effect which is intended, or at least our models predict that they don't have exactly the effect for which they were intended. And maybe our models are wrong, but at least I think that's some interesting input one could give. No, yeah, I think that's a very good point. So given some market segmentation, you can define the consumer surplus, which is just whenever a consumer is buying, their value minus the price they're paying for different types of consumers. And you can define the deadweight loss as just those consumers who don't buy times their value because the production costs here are zero, so you could have given the product to these cost consumers, they don't get it, so that's the deadweight loss for that type of customer. And so the regulator is presumably interested in like the consumer surplus of these different groups and potentially also the deadweight loss induced by the legislation. Any questions before I kind of show you the optimum?
Philip, I'm sorry, I was going to type a question, but then I typed too slow. It's probably easier if I ask
yeah, please.
verbally. So this is a very tight notion of non-discrimination, and as you just discussed with Laura, it might have some unintended consequences. And one could think of something a little bit more weaker, like it's not discriminatory in expectation or something like that, rather than over the whole distribution. Is there possibly a sense, I don't know whether you looked into that such that actually applying that weaker notion would lead to better outcomes, at least in some sense?
That's a good question. I like, so I think a natural weaker notion, which I think also is compatible with the law, is that you are actually allowed to condition on some things which are deemed materially relevant. Whether this leads to better, I mean, and mathematically, that's essentially the same problem as I'm going to describe to you. It's an immediate corollary of our solution to find the solution for this weaker notion. You can probably define many other notions, like they could be, I don't know, instead of exactly the same distribution, you could now use some distance or measure on distributions and say they cannot be too different, or you can make this hold instead of point-wise in some average sense. The analysis, so we didn't analyze any other notion, so I cannot tell you whether this would lead to better outcomes. I think these are interesting questions because I think by studying what such a law will do, we maybe can also inform the law how it should be written to kind of lead to desirable outcomes. But
because you have a natural notion of welfare here, right? Exposed. You could just add up the welfare exposed, and you can say, I'm going to change the definition and I'm going to maximize over the definitions. And it's not obvious that the one that's being proposed here is the optimal one. Yeah.
Yeah, I think that's a nice exercise. We didn't do it, but I think there's a nice exercise one could do in thinking about what notion do we actually want. So we tried to model the notion which, as we understand it, is currently used in the US, but probably there are other notions in different countries, and it makes a lot of sense to think about what's an optimal notion. I mean, that just seems supernatural to me.
Okay, thanks.
Other questions? No? Okay. Maybe then let me show you the optimal non-discriminatory segmentation. So first, relatively immediate lemma is that a market segmentation is non-discriminatory if its outcome equivalent to market segmentation that is independent of theta. In some sense, the prices based on theta need to be independent. The prices based on S need to be independent of theta anyhow. So we could just as well make S also independent of theta, and I'm not losing anything by that. And so this is then exactly equivalent to the notion of privacy preserving signets, which we developed in a previous paper. And so here, to describe to you a solution to the problem, I am I give you this system of equations, and there's nothing you need to take out of it apart from that these 4 numbers always exists. Like if you solve this system of equation, you get like 4 cutoffs. They always exist and they're always ordered this way. And I'm going to use the cutoffs in the solution a little bit later. I just wanted to define them once formally, but it's just saying they exist 4 cutoffs, they're ordered this way, and I'm going to use them in a moment. And you don't need to look at exactly what they are. Like I will show you pictures in a second. Yeah, but now these cutoffs are defined. And so now consider 2 groups. We are going to consider the following segmentation. Suppose these are the densities of their value distributions. This is a complete description of the joint distribution. Now, if I tell you what the probability of theta equal to 1 and theta equal to 0 is, we're going to now introduce these cutoffs, which were defined on the previous slide. And now we're going to match people together. And each segment is going to consist of exactly 1 person from group theta equal to 0 and 1 person from group theta equal to 1. So these are like small segments where there are just 2 types of customers in each segment. And first, we are going to take customers between this cutoff V lower bar and W lower bar and V upper bar, and we are just going to match them exactly when they have the same value. So now in these segments, there's a high value customer with value, let's say 0.3, and a low value customer with value 0.3. The optimal price I'm going to charge in such a segment is, of course, 0.3 there. And so I do this for as many customers as I can. Then I'm going to do the same at the top of the distribution. The very high value customers, I will again just match if they have exactly the same value across the 2 groups. So what I then will do in addition is I will take some of the low type customers who have very low values, and I will match them assortatively with the high value customers. So what does this mean? Now I have someone from the group with a high willingness to pay and someone from the group with a low willingness to pay matched together in a segment. And what the seller will do in this segment is he will just charge a price equal to the value of the high type customer. And then the low type customer, and this goes back a little bit to your question, Daniel, will self-select into not buying. And then, so this will happen in this yellow segment. And then we will have another segment between V lower bar and V upper bar, where we will actually match low type customers with relatively higher values with high type customers with relatively lower values. And in this segment, the seller will be charging the higher value, the value of the low type customer. And now, in addition, we are gonna have this interval here, which is between V upper bar and W upper bar, and here the seller is gonna match assortatively. And because of the monotone likelihood ratio property and how these cutoffs are exactly defined, it's going to turn out that the customer of type 1 is always going to have a higher value than the customer of type 0. And it's going to be optimal for the seller to always charge a price equal to the value of the low type customer. And so here the high type customers are going to get some surplus because their value exceeds the value of the low type customer, which is going to be the price in this segment. And so this is one way for the seller to divide up the market. It's kind of complicated, and that's turns out to be an optimal way of doing it.
And is it uniquely optimal?
It's not uniquely optimal. I will show you all optimal ways of doing it a little bit later. But this gives you a bit of intuition. If I start by showing you all of them, then this will easily get very confusing. But all of them look very similar to this one. So there's not much wiggle room here. And I will show you a proof why this is optimal, and then you will see after the proof, it will become clear that there's not much you can do otherwise.
Okay.
And so this is always the structure the seller is now going to use to kind of segment the market if he doesn't want to discriminate between the two groups. I mean, this is kind of a complicated solution a little bit. So any questions about how it works?
Yeah, Philip, can I ask something quickly? Sorry, can you hear me?
Yes.
Excellent. So if I understand correctly, this is going to induce, there's no correlation between the prices faced and theta, but there'll be correlation between the prices at which the people who buy at and theta. So I'm just trying to think about how the legislator is going to look at the data here, because if you collect data on actual sales, is it going to look discriminatory?
Yeah, so this is going back to the question of self-selection. You could do this with a different notion where you would want to have no, like you want to have people face similar prices conditional on purchase decisions. And I think that is not like a completely different problem, but so yeah, so I guess it's hard for me to answer the question how the legislator would think about this.
I'm just worried if I'm a company that's trying to prove I'm not being discriminatory, you know, I can't rely on sales data. I've got to rely on like prices that are faced, and that seems a little bit murkier.
Yeah, I think that's a fair point. I think this is just like, yep, I would be happy with that. And in some sense, that just motivates the other exercise to do it conditional on prices at which things are sold.
Okay, but you think everything would work fairly similarly?
We didn't do the exercise, but my guess is similar methods would work to do it. And yeah, I think all of these are interesting exercises, and kind of exploring this whole space just seems interesting to me.
Okay, thank you.
Can I add something here? Because
Yeah.
that's a very interesting question, and I think it depends on what kinds of product we're looking at, right? If it's commodity, then it'd be easier to collect sales data. But if it's a product offered by an online platform, say Uber, then you could also Uber would also have data that they offer to everybody's cell phone when they request a ride, unconditional of whether they have taken the ride yet. So it depends on the context, and it depends on which product we're looking at.
I mean, maybe to elaborate a little bit on this, I mean, we make this rich data assumption, which essentially already is moving a lot towards online products, where you have all this rich consumer data, and there it might be just like that very often we just keep track of the offers we make. Yeah, but I don't think the other question is uninteresting. Other questions? No? Thank you. Okay, perfect. So now this is just kind of summarizing what I just said. So there is an optimal non-discriminatory segmentation. So S star, which is the segmentation described just before, is an optimal non-discriminatory segmentation. Moreover, under this segmentation and any optimal pricing rule, the surplus of low-type consumers is 0, and the high-type consumers get surplus in this interval where they are assortatively matched, and the surplus they get there is just this integral written out. And then you get the corresponding deadweight losses from not selling to consumers in these two segments. Yeah. So here, maybe this goes already back to the point Laura made, which is that this legislation really gives no surplus to the low-type consumers. And it's not completely clear. I think it depends on the application whether the low-type consumers are actually the consumers which should benefit from the non-discriminatory law. Like in insurance context, these might actually be the high-type consumers sometime, and then the legislator might be very happy with this outcome. But in other contexts, this might, like in the credit card context, the theta equal to 0 might actually be the segment of the consumers the legislator cares more about, and he might actually be not happy with this outcome. Yeah.
Sorry, I have a question. Then perhaps at this point it's a good moment. So here you assume that the seller in some sense lacks the commitment power. So in a sense, for whatever you learned about the consumers, you'll be charging optimally. You could consider an alternative setting. What if the seller could commit to how you price different types of consumers, subject to the restriction that, the same restriction that you have of non-discrimination?
So the seller here can commit to it. I see. So you are saying that, but I could just have the signal be the price directly.
So you think it would be exactly the same solution?
Yes, I think so. Because the signal could reveal nothing more than the price. Now, and then.
But here you have incentive constraints that you have to deviate once you learn something, and they would not have those incentive constraints necessarily.
Exactly. So once I only reveal the price to the seller in this segmentation, I could just label each segment with a price.
Alex, our objective is entirely consistent with the obedience constraints. So may as well.
I see. So there's nothing.
We're maximizing profit, so we may as just.
Okay, so it goes the same. Okay, great. Because it seems an alternative benchmark also to have in mind. Okay.
Yeah. So we later on, if we think about welfare, which we are working on, where the objective is not profit, but the seller, like there's some different objective of this segmentation. So the person choosing the segmentation, there it would make a difference. So that maybe the legislator can choose the market segmentation instead of the seller. And then I think this would make a difference.
Okay, thanks.
Thank you. Okay, let me give you a sketch of the proof. And so a segmentation is conditionally revealing if learning the market segment and whether it's a low or high type consumer actually reveals the value. So this is a bit of a hypothetical thing because you might not learn whether it's a low or high type consumer. The seller only learns the market segment. But if he, in addition, were to learn whether it's a low or high type consumer, then he would perfectly learn the value. So this means just that we essentially have two values in each segment, one for each type of consumer. And this was a feature of the optimal segmentation I've just shown to you. And indeed, this feature is without loss. So a lemma from our earlier paper shows that every non-discriminatory segmentation generates a weakly lower profit for the seller than some conditionally revealing non-discriminatory segmentation. So you only need, in each segment, you only need to consider one low and one high type consumer with different values. And And so now we have these vectors V0 and V1, and we already know their marginal distribution, right? We know the marginal distribution of low-value consumers, and we know the marginal distribution of high-value consumers. And now what we essentially want to do is we want to pair them up. And that's exactly an optimal transport problem, which means that we have fixed marginals, and we are looking for a joint distribution where we pair one low-value and one high-value consumer. And we are going to look at this optimal transport problem to actually solve and find a solution of our pricing problem. But this was an insight from our earlier paper that this way you can transform it into an optimal transport problem. So let us denote by a row the set of joint distributions over the kind of value space, the space of value squared, which have exactly the right marginals, like the low type and high type marginal distribution. What is the profit I'm getting from pairing a low type consumer with value V0 and a high type consumer with value V1? Well, in each pricing segment, in each market segment, there are just three possible prices the seller could choose. He could either choose a price equal to the value of the high type consumer, to the value of the low type consumer, and sell only, I mean, suppose the high type consumer has the higher value, which is not true always in the optimal segmentation, but suppose it's true, then the seller decides between selling only to the high type consumers or selling to both of them at the price equal to the minimum of their two values. Okay? So the seller can sell to both of them at the minimum of the two values. So that's the price he can charge and sell with probability 1. Okay, he can charge the higher price, let's say V1, and only sell to the high type consumers. And so given each market segment, which only contains two values, this is the profit the seller can make when charging an optimal price. And here we use that each segment only contains two values. I mean, the seller could charge prices in between, but they will lead to strictly lower profit because he could increase the price and sell just as often. So these are the only three possible candidates for the seller's profit, for the seller strategy. And so then this is his profit. And so now we have completed this into an optimal transport representation. We are searching, so the profit is the maximum over these joint distributions with correct marginals, where the transport function or cost, how they call it in the transport literature, is exactly the profit function. Any questions? No? Okay, so and now let me maybe discuss a little bit how this relates to other optimal transport problems, because I think there's an interesting relation here. So to just get an intuition for this, assume that half the consumers are high types and half are low types. You can make a similar argument in general, but it just makes the algebra more complicated. So instead of maximizing profit, we can just add half of the available surplus minus profit and minimize this, because in the optimal transport literature, you often want to minimize the cost. So I want to kind of get closer to the problems they look at into this literature. And then if you just do some algebra, it turns out that the profit function can be rewritten like this. So it's half the minimum of the values of the two consumers and their distance. And so the typical optimal transport problem is just the distance. So now we have this minimum with the two values in addition. So this is the just very classical optimal transport problem where you just look at the distance. And what does it look like? Well, this looks like this. If you plot this function, and this objective, as you can see, it's non-convex, it's non-concave, and it's not translation invariant. So like essentially all the optimal transport literature is focused on things which are translation invariant. And a lot of them look at the concave case in which we know we want assortative matching. In the In the convex case, in the concave case already, this is much harder to understand. Just as a frame of reference, the only other paper which we know kind of looks at these more or less non-standard optimal transport problems is a paper by Borma, Zwinsky, Wang, and Zhang, who consider the case of the distance between the values to some power less than 1, which is like some quasi-convex objective where you are concave on each side of the minimum. But that's already translation invariant and has many nice properties. And even there, like they show something about the optimal solution, but characterizing the optimal solution turns out to be very hard. So in general, these problems turn out to be not completely obvious in their solution. Any questions about this? Okay, so then let me move on. So how are we going to solve this now? We are going to use the duality approach from the optimal transport literature. Instead of looking at the primal problem, a known result in the optimal transport literature is that you can look at the dual problem, where you now have to minimize over two functions, which are only functions of one of the variables. And you minimize the sum of the expectations, but you're subject to the constraint that the sum of these functions must be pointwise greater than the profit. And
Philip?
Yep.
Sorry, I probably should have asked this earlier, but in that picture, like sometimes in optimal transport, what they do is some sort of like they convexify the cost function, like they reorder it so that it looks. Would that help?
You can't do it here because then also the solution would be some assortative matching, which is not optimal here. But I don't see a way of convexifying this here. It's also not translation invariant. I mean, this cost function, if I go back, I plotted it here for V1 equal to 3, but it's not just, you cannot shift it left and right without it changing.
I see.
So the convexification trick, I can't even see how to do it in the non-translation invariant case. But yeah, I might be missing something.
No. Thank you. This is useful.
Sorry,
thank you.
Philip, I'm sorry, since there was a question, I'm going to ask another one, which is much more prosaic. I'm not sure I understand the picture. So you have V2 here, which is what?
Oh, sorry, this should be V1 and V0. I switched. This should be V1. Sorry.
V1, okay.
Or V0. Yeah.
I'm sorry. I thought the valuations were between 0 and 1. Did I miss something or no? They're not.
Oh, sorry. Then I made a bad picture if I assumed this before. Now they're between 0 and 10.
No, I don't remember myself. Okay.
So no. So now here it's between 0 and 10, and one of the values equals 3. Let me maybe walk through the picture to make it clearer. So suppose the value V1 is 3, and I plot on the x-axis V0. So sorry, I'm sorry for the typos on the slide. So this should be V0. Then first, the minimum is at V0, and so you have the identity function up to some point where then the distance between V0 and V1 is actually less than the value of V0, which happens at 1.5. And then if V0 further increases, the minimum is going to be attained at the distance, which means it's going to decrease until the distance becomes 0, which is exactly at 3. If V0 then increases further, the cost goes up until the point where actually V0 the distance becomes greater than V1, which is 3, and then it stays bounded at 3 because it never goes above V1.
Thank you. Much more clear. Thank you.
And no, sorry, this was my mistake. And so this is very different from the typical cost functions looked at in optimal transport, which are typically assumed to be convex or convexifiable in some way. And then, I mean, typically also monotone, moving away from a minimal point. So this is not monotone. It's just very different. Yeah. Okay, so let me other questions. Sorry, these are actually very useful questions. Okay, so then so we are going to take a dual approach, and so there's this known result of Kantorovich duality, which tells you that in fact solving the dual problem gives you a solution to the original problem. And so we're going to solve this dual problem. And the solution we do is we're just going to guess the duals, and we're going to prove that these are indeed the duals. And this is a bit of a lengthy exercise. And how did we find them? Well, we ran a lot of computer simulations and solved special cases and thought about it. And yeah, so there's no systematic approach to this. So it just was like mostly banging our head against the problem for a long time. And so here are the duals. There's nothing too interesting in looking at them. And they're defined in these intervals where I already gave you the cutoff for these intervals. That's what they look at and what they look like. I leave them there, but really there's nothing too interesting to see in them. It's just they're certifying that this is indeed a solution. And the first lemma is that indeed these are valid duals. And then you can now look at where the duals equal the profit function. So the support of the optimal transport row must be included in the set where the duals equal the profit function. So we can now, given that we found the duals, we can plot the regions where the duals equal the profit function. So we know that so this is now a picture where on the x-axis we have the value of the low-type consumer. On the y-axis we have the value of the high-type consumer. And the optimal transport is going to be a pairing of these values. And we know that the optimal pairing must be kind of supported in the area where the duals equal the profit function, which is just the area which I marked for you in red. And so now here you can see the support of the solution I've shown to you as initially where I showed you one optimal solution to the problem. But what you can also see is that now there's some wiggle room, right? You can move some of the points up or down and not affect the profit. For example, in this intermediate region where I matched assortatively one high type and one low type consumer, the high type consumer always has the higher value than the low type consumer. So there's many different ways of matching them together. And in fact, any way where I match such that the high type consumer has the higher value than the low type consumer here will be such that the sum of duals equals the profit function. So I can match them in a different way. This will change the values of specific types of consumers with specific characteristics and value, but it will not change their aggregate profit, which is just the integral over that interval. So there's some choice I can make about how exactly I'm pairing these people up. But in this interval, for example, choosing a different way of pairing them up will not change their surplus, the aggregate surplus for the different groups. It will change the surplus of individual values, but not of the aggregate over the group. And so there's one region where I can actually affect the surplus, and that's the region here where I can essentially, instead of having this overlap, switch around a little bit and choose which consumers I match upwards. And like here, you see the yellow and the blue area overlap. So here, this is a yellow area and this is the blue area. In this region, I can take some of the low willingness to pay consumers and move more from here to here, and instead match them slightly more profitable for the other type, and that can generate a little bit more surplus for the low type consumers. And that's kind of our next result. Recall that we define the consumer surplus and date weight loss we say something is a surplus outcome if there exists some non-discriminate segmentation S and a pricing rule rho such that indeed this surplus and deadweight loss is induced. We define this type. And so something is a surplus outcome if and only if the welfare of the low type consumers is between 0 and some upper bound, sigma 0 upper bar, which we can explicitly construct actually the segmentation which corresponds to that. And the surplus of the high type consumers is always fixed. So it doesn't, in the optimal market segmentation, the high type consumers always get the same surplus, but there's some ambiguity about the surplus of the low type consumers. And there's a lot of ambiguity in the segmentation, but this ambiguity is not welfare relevant. And so any point in between 0 and sigma 0 upper bar is exactly the welfare which can be induced for the low type consumers. And then there's like corresponding bounds on the deadweight loss for the low type consumers. So this goes back to the question which was there a bit earlier about whether there's uniqueness. So there's no uniqueness, and especially there's kind of the welfare of low type consumers can change throughout which segmentation, optimal segmentation is chosen. How much time do I have? Sorry.
Maybe 4 or 5 minutes.
Perfect. Then let me maybe just speed up a little bit. So now what does this mean? So one question we are interested in is, and a lot of people already ask about, how do these anti-discrimination regulations affect actually consumer welfare? And so here we have a table where we look at kind of different conditions. So the first one is the case where the seller only sees the protected characteristic and nothing else in data. So I only see if I face, let's say, a male or a female. And I consider the two cases whether either I'm allowed to discriminate based on gender or I'm not allowed. And then you can see that the high type consumer surplus goes up if discrimination becomes forbidden because they now will face lower prices. The low type goes down because they will face higher prices, and similar things for the deadweight loss. And now the focus of our paper was personalized pricing, where the seller has a lot of additional data and can actually predict the values. Like we are taking the assumption of Bergerman, Brooks, Morris here. And there you have to distinguish which equilibrium or which segmentation you look at. If you take the least efficient segmentation, then the consumer surplus of the low type is always 0. The consumer surplus of the high type consumers actually goes up through anti-discrimination regulation because it will mean that they will face, they will get some surplus which they would otherwise have not gotten. And if you take the most efficient market segmentation, then both low type and high type consumers actually benefit from anti-discrimination regulation. So if you focus on the most efficient market segmentation, I mean, they are all leading to the same profit for the seller, then both type of consumers benefit from it. Also for both types, the deadweight loss increases. And you can finally ask who benefits more from that regulation. And that might be either the low type or the high type who benefits more in the most efficient segmentation. So we cannot tell you who is benefiting more, but we know that if you take the most efficient segmentation, both types of consumers will actually benefit from this anti-discrimination legislation. Now, maybe as a last exercise, and then let me maybe just tell you one thing. We actually don't know who's getting more surplus in these markets. Even though the high value consumers have higher values, it might be that if most of them are high value, the seller will actually be targeting them and kind of adapting the optimal segmentation to them, which might lead to them getting very low surplus. And vice versa, if there's a lot of low type consumers, the seller might be targeting them and might make them get low surplus. So it depends on which fraction is high or low type consumers who is going to get more surplus. Even though the low type or high type consumers might a priori have higher values, that doesn't mean that they're getting more surplus. It depends on the ratio between the two groups, which, yeah, that's maybe obvious ex post. And let me skip examples. So I gave you a model of anti-discrimination regulation with personalized pricing. Sometimes in some market segmentations, actually low-value consumers may not benefit from anti-discrimination laws. Some deadweight loss. And it could be that low-value consumers could even benefit more than high-value consumers. It depends really on the ratio of these consumers. Like essentially what the seller starts doing is he's targeting the larger group. So if one group is very large, he's just, this is very bad for that group. And extensions we are working on is like consumer optimal segmentation. So what if kind of a designer chooses these segmentations to benefit consumers? We are thinking about some models of interdependent values. And we are thinking about incomplete information for the seller and have some simple examples here. And yeah, and I think there are many other interesting questions around this. You could, like, someone made the very good suggestion of thinking about what if it must be conditional on sale, the same distribution of prices.
Thank you very much, Philip. So maybe now a few comments from our panelists. Laura, do you have any comments or questions?
Let me stop sharing.
So first, thank you. I really like the talk. Sorry for I aiming to jump ahead before. I was one thing that was not immediately clear is what was the role of the likelihood ratio ordering across the distributions, except that we could say like one population has higher likelihood of having higher values, and in many of the segmentations, the seller is actually trying to target the higher value consumers. But other than like, I guess I from the how the distributions affected the construction, that was something that was not immediately clear.
Yep, I didn't explain it. It was, sorry. So
no,
actually,
no. I guess it's more general than that. I guess that this is what I was coming from. Like I couldn't see except like from this order, it seemed like things were more general.
So what's going wrong? Sorry, yes.
No.
So the economic reason we assume it is we want to really assume a higher elasticity of the low type consumers. So for that reason, we think it's reasonable. Where we use it mathematically is in the part where there's assortative matching in the optimal segmentation. In the assortative matching, the higher value is always the high type. In general, this need not to be true for the assortative matching because we are not comparing, we are comparing kind of distributions where we took away some part and conditioning on being above a threshold. It need not to be true that the same ordering holds. And that is actually part of the proof why these are correct duals. Otherwise, these are not correct duals. It turns out the optimal transport solution might get much more complicated.
I see.
And then, yeah, we have some simulations, but we think it's actually without the MLRP assumption, it's probably impossible to characterize. So we banged our head against this for some time, and it just becomes, yeah, I don't know what the solution is. That's the honest answer.
And then I guess eventually you guys will be able to have like a picture of the Bergman-Brooks-Morris triangle.
We have this picture.
I didn't show it to you. Okay.
Yeah, so this is a good point, and we are working hard. We can do it for 2 values analytically. We have a solver for n values, and we are like, the problem here is that actually the problem is much harder than the profit maximizing problem, because now it's a Bayesian persuasion problem, exactly for the reason Alex mentioned, that now the objectives are non-aligned anymore. And that actually makes it a much, much harder problem. You might now, it's not so obvious that you only want to put 2 types into one segment, right? You now want to use these equal revenue distributions all over the place. And the solution changes in nature to some extent. Because it's now a persuasion problem really than an optimization problem. So the point which is an optimization problem with profit maximization, at the other points, you now have to worry about incentives for the seller. And so we can do it with 2 types, a bit by hand. With n types, we can do it numerically, and you get really a subset of the Bergman-Brooks-Morris triangle, which it's just like, it is actually you cut off the corners and you have some rounding inside. It looks nice. I should show a picture, but we don't have an analytic solution for more than 2 types. And I don't know if that's at all feasible. It probably requires a different methodology.
All right. Thank you.
Thank you. That was a great question.
Thank you, Alex.
Okay, likewise, I very much enjoyed the talk and the paper. I think it's really interesting and important area that you're working on. I think regulators should think more about these questions. But I have a question. I mean, I guess it's an obvious one, but so what happens if you have multiple these protective characteristics, right? I mean, and I understand that the general solution will be very complicated, but I was thinking whether you thought a little bit some qualitative things. So first of all, like if you have the rank by MLRP, so what can you tell something about the surplus of the lowest value of characteristics? Perhaps it's 0, perhaps not. And second, what if you have just actually concentrated types, right? This is the simplest case. So if you read each characteristic, actually the value is pinned down. So would it be true that you have then single posted price being optimal once you impose non-discriminatory things?
So this is a good question. So I think we know a little bit about what happens with more protected characteristics. What is still true is that the solution is an optimal transport problem, but now you have for each characteristic you choose 1 value, so it becomes like instead of having 2 marginals, you now have 3 or 4 dimension with fixed marginals.
Right. Yeah.
My worry is that the complexity of this will just explode a little bit.
Yeah, so I wouldn't count characterizing full solution, but maybe you can have some qualitative properties, right? For example, again, 0 surplus. But the other part, right? When there is 1 value for each characteristic, that should be easy one, I would imagine.
Where there's 1 value only for each characteristic?
Yes.
Sorry, I'm now confused. How would that case work?
So you have several characteristics, and that characteristic has that value.
I see. That might be easy.
I guess it must be easy. But so conjecture that it probably will be posted price then, but maybe not.
I think that's I share your conjecture that that's the solution in that case.
Right.
So and economically, what you're saying is just if there's enough characteristics at some point, it just makes price discrimination completely powerless, right? It doesn't do anything anymore.
Exactly.
Once I have enough characteristics. Yes, I think that's a nice point to make. Yeah, thank you.
Yeah, because and then it would lead to posted price, because I guess it's very often these regulators have in mind that if you regulate enough, then you just force posted price and somehow.
Yep.
Same treatment for everyone.
Yep.
In some sense. Yeah.
Okay, great. So I think we can stop now the official part of the talk and stop the recording.